Welcome everybody to today's One World Mathematical Physics seminar of the International Association of Mathematical Physics. We are very happy to have Marino from the University of Geneva today, who will speak about trans series in quantum field theory. Please, Marcos, go ahead.
Okay, thank you very much for the invitation. So let me first start with a warning, which I already communicated to the organizers. I'm not a mathematical physicist in the sense of being a rigorous mathematical physicist. So what I will follow is not going to be rigorous. Some parts can be made probably rigorous. Some parts I know they can be made rigorous. But the style of the talk will be more like theoretical physics or even experimental mathematics style, okay? Okay, so I will talk about trans-series in quantum field theory. This is related to the subject of resurgence that people have looked at it recently with a renewed intensity, but many of the ideas that I will cover are relatively old. Especially I chose to talk about quantum field theory where many of the ideas are well known and the progress has not been that spectacular. I think most of the recent developments in resurgence have led to more spectacular results in the context of complex Chern-Simons theory or topological string theory. But in quantum field theory, the results are probably more modest. But probably from the point of view of philosophy, I think this is an interesting development. Okay, so let me start. Okay, so let's start with perturbation theory, because this is actually the basic tool that we will use in this story. So perturbation theory, of course, I don't have to convince you of how important it is. It's actually a relatively universal tool we have in quantum theory. But unfortunately, typically the perturbative series that we find in quantum theory, in quantum mechanics, and in quantum field theory, the typical series actually grow factorially. The coefficients grow factorially. So you compute an observable as a function of the coupling constant. Here, even after normalization, you will get that the coefficients grow like n factorial. And then in principle, this means that the series cannot be used to calculate the observable. What they give you is something different. They give you the asymptotic behavior of this observable at a small g. And this is what asymptotics means in the sense of Poincare. Okay. Now, of course, people do use perturbative series to do calculations, but there are various techniques to do that. In a sense, the kind of more primitive one is what people call optimal truncation. So essentially, the idea of optimal truncation is that, of course, you cannot keep all the terms in the series. So you try to keep the maximal number of terms that give you the best approximation to the answer, okay? So that's an approximation. It's an approximation in which, the bigger the coupling constant, the worse is going to be the approximation. It's an approximation which always has an exponentially small value, okay? Now, you can try to go beyond optimal truncation. And for doing that, you can use resummation techniques. And the most well-known technique and the most useful one is perhaps Borel resummation. And since this is going to be central to this talk, let me remind you a little bit how Borel resummation goes. Okay, so in a sense, you can think about Borel resummation as the sequence of two operations. So let's suppose that you have a factorial divergent series. So here is a formal series in which an go factorially. So the first step of the procedure is to do what is called a Borel transform. And the Borel transform is kind of very simple. You just try to cut out the factorial growth by dividing every coefficient an over n factorial, and you create a new series in a new variable that I'm going to call zeta. Okay, zeta sometimes is called the Borel variable. Okay. Now, once you have constructed this series, this series essentially by construction has a finite radius of convergence because you have cut out the higher growth of the series, which is factorial, and then you do a Laplace transform. And this Laplace transform is an integration of this Borel transform with an exponential kernel. And if this integral converges, which is a big if, then you say that this integral is the Borel resummation of the original series. And when this integral exists, the asymptotic expansion of the function that you have defined actually coincides with the original non-perturbative series. So in a sense, you can think about this procedure as a way of making sense of factorial divergent series and converting into functions, okay? So this procedure actually, as I said, has to be taken with care, because also the Borel transform is analytic. When you analytically continue to the complex plane, you can find all kinds of singularities, okay? But in general, it's an interesting procedure because, in a sense, you have gone from the world of totally meaningless formal power series with factorial growth to the world of analytic germs at the origin. So this is an improvement. Now, one assumption that is sometimes made is that the Borel transform can be analytically continued to the whole complex plane, or at least to a neighborhood of the positive real axis, or to the axis where you're going to eventually do this integration without by analytic continuation. So you assume actually that you can actually do this analytic continuation. For example, you assume that you don't find, say, walls of singularities that make this analytic continuation problematic. Okay, that's an assumption that I will essentially keep in mind in the following. Okay, although it's not completely strictly necessary for what follows. Now, this Borel resummation procedure has historically some very successes, some very interesting successes, and maybe the one which is probably better known to the community of mathematical physicists is the famous quartic oscillator in quantum mechanics. So we take the harmonic oscillator, we perturb it by a quartic term, the x to the 4, and if you consider, for example, the formal Rayleigh-Schrödinger series for the ground state energy, you will find typically, you will actually find a factorial divergent series in G, okay? Oops, sorry, whose coefficients can be computed relatively easily. And it's actually a theorem that this series is actually Borel resummable, and the result of the Borel resummation gives you the exact value of the energy levels. Okay, so you can do this actually level by level. Here I just wrote you the result for the ground state, but you can actually do it level by level. So this is a kind of famous result of Graffi, Grecki, and Simon, and this is a success story for Borel resummation. Now, there are, however, cases where this Borel resummation procedure is not conclusive. Okay, and let me tell you what is the most typical source of problems. The main problem is what happens when you have a singularity on the positive real axis. Okay. Now remember that if you go here, when you go from the Borel transform to the Borel resummation, you have to integrate your Borel transform over the positive real axis, and if this Borel transform has a singularity there, you won't be able to define this integral. Okay? And this is actually the situation in which people in which traditionally you call this type of situation a non-Borel summable series. Okay, and actually, in a sense, I think what happens in a sense in these two different communities, the community of more traditional mathematical physics and the community of resurgence, is that traditionally non-Borel summable series in the math physics community were regarded typically as hopeless. I mean, you have an obstruction to this integration, you just say that your series is non-Borel summable, and you do something else. But actually, in the resurgent community, in a sense, people try to push this resummation program by doing two types of modification in this program. So the first one was to consider a generalization of Borel resummation, which sometimes is called Borel-Ekal resummation. And the second modification is that instead of considering just the original perturbative series, you consider what is called a trans series. And this is, in a sense, a way to fix the problems when you have a non-Borel resummable perturbative series. So let me tell you how this goes. And so let me first try to define, this lateral resummation or Borel-Ekal resummation. So let's assume then that you have a typical obstruction to Borel summability in which you have singularities along the positive real axis. Okay, so the standard Borel resummation is ill-defined. Now, what you can do is to try to deform your integration contour either above or below the positive real axis in a way in which you avoid the singularities. And the integrals along the upper or lower contours are called the lateral resummation, the upper lateral resummation or the lower lateral resummation. So they are defined in this way. So you keep the same definition by just deforming the contour. Now, of course, this is a problem, right? The problem is that well, this now is well defined, but you have two answers instead of having one. So the price you have to pay in order to fix the problem with the singularity is that you will have now an ambiguity because you have two paths of resummation, and this is sometimes called the non-perturbative ambiguity for this problem. Okay. So what is very interesting is that the difference between this lateral resummation is typically an exponentially small quantity and measures in a way the nature of the singularity. So let me give you a very simple example. Suppose, for example, that the Borel transform has a simple pole at a given position zeta equal to A. Now it's very easy to see then that when you take the difference between these two lateral resummations, you just pick the residue of this pole in this Laplace transform, and then you get actually something which is exponentially small. Okay? So this is the typical non-perturbative effect that we find in quantum theories, in the sense that this is exponentially small in Z, and this is non-analytic and Z equals 0. And let me also point out that the location of the singularity, remember that here we are considering a pole as Z equal to A, gives you the strength of the exponential term. Okay, and of course this is the case for this case in which the singularity is a pole, but it's also the case for more general types of singularities. So singularities along the integration line get reflected into exponentially small terms in this discontinuity, in this difference between these two lateral resummations, and the location of the singularities gives you the strength of these exponentially small terms. So the farther your Borel singularity is, your singularity in the Borel plane is, the smaller is this correction. Okay, this thing. Now, what people do, it's to actually think about these terms as smoking guns for non-perturbative corrections, which you have to include explicitly in your theory. Okay. And mathematically, the way you are going to include this in these exponentially small corrections is through the object called transseries. So I'm giving you here all the ingredients, but later on in a moment, I will give you a very concrete example in quantum mechanics to see how this works. Okay. So the idea is that this, which is a problem for a standard Borel resummation, these sort of ambiguities, are going to be smoking guns for something that you are missing from perturbation theory. Okay. So, the transseries formally are obtained as follows. You just these are formal objects in which you just take your original perturbative series and you add a formal infinity in principle linear combination of other formal perturbative series with an exponential term of this form. So these are enlargements of your original perturbative series in which you consider, in a sense, an additional small parameter. So you have Z as a small parameter, and you have exponential of e2 minus a over z as your additional parameter. Here I'm considering a particular case in which all singularities occur as multiples of a single position A. But in principle, you can consider a very, very general object in which you have, an arbitrary sum of exponentials with all, whatever exponential you want to have here. And you have attached to these exponentials series, which are also factorially divergent. Typically, these series look like this. So you have an additional series in Z. You can have a prefactor, and ALN also grow factorially with n for any fixed L. Okay. So transseries are very, very formal objects, but physically they have a very clear interpretation. They correspond to adding non-perturbative sectors to your theory. So you started with your perturbative series, but now you will try to add non-perturbative sectors in this way. And some of these sectors might actually reflect the singularities or the singularities that you find in your Borel plane. Okay, so So that's the kind of philosophy that people in resurgence do. So you see, you are not stopped by the fact that the series is non-Borel summable. You just think about non-Borel summability as a smoking gun for additional things that you have to add. Now, actually, transeries have been
question.
Yes.
BL has to be can be fractional, or it has
Absolutely,
to be...
absolutely. That's the point. You know, sorry. So BL is typically fractional. Yes.
Fractional. Okay, thank you.
Yes. I mean, you know, you can have this can.
Okay.
Yeah. Otherwise, I mean, if it's, I mean, it can be a negative integer, but it can also be fractional. Absolutely.
Okay, thank you.
And in real life, you know, these are typically fractional numbers. Okay.
Okay, thanks.
Now, transeries are actually well understood in a very interesting case. So you have never seen them. It's actually easy to see them when you study ordinary differential equations near irregular singular points. So let me give you a kind of very simple case here. So suppose that you have the Euler equation here. Okay, that's a very simple first order equation. In which you have an irregular singular point here around x equals 0. So you can actually construct a perturbative solution at x equals 0, but of course, since this was an irregular singular point, you will have a factorial growth in the coefficients. Actually, in this case, you just have n factorial. Okay. Now, in the transeries solution, you actually add to this perturbative part an exponentially small term of this type with an arbitrary coefficient, and you can actually check that this is also a solution of the original equation. Now, C actually here is parameterizes the kind of the boundary condition that you have for this first order equation. And the idea that people developed in the study of ordinary differential equations for irregular singular points is that you might actually construct actual solutions to the ODE by doing actually Borel resummations of these factorial divergence series. Okay, and you can actually prove, and this is something that I think has been. I mean, there is some debate about how much has been proved, say, by Ekal himself, but there is more rigorous work, for example, of video costing that shows that for general, for very general classes of nonlinear ODEs, and also very general classes of solutions, you can actually write these general solutions as Borel-Ekal resummed transeries. Okay? So this is, in a sense, you can think about the theory of nonlinear ODEs as the kind of role model for what we would like to do in other contexts like quantum field theory, quantum mechanics. So, for example, this has been developed very much for Painlevé type of equations. Okay. Now, let me give you a kind of more physical example of how transeries are relevant. And in order to do that, I'm going to consider one of the simplest examples of a non-perturbative effect in quantum theory and of a non-Borel summable perturbative series. So this is just the famous double well potential that I wrote here. So you want to consider you can actually calculate formally the ground state, the perturbative series in the coupling constant G for the ground state energy in a kind of similar way to what happens for the quartic oscillator. And you can write down many coefficients. And one thing that it's very easy to see is that this series is actually not Borel summable. So there are singularities on the positive real axis. So you try to actually calculate the ground state energy by resumming this series, you don't get the right answer. So then you can try now to move to these lateral resummations. But of course, if you do these lateral resummations, since you are jumping over the poles or under the poles, you will get an imaginary piece by the contributions of these singularities, and these are physically unacceptable. These are exponentially small imaginary pieces, so you cannot just you take this series and do the lateral Borel resummation. This is not the solution that is proposed. So the solution that is proposed that you have to take this series, do the lateral Borel resummations, you will get imaginary pieces, but then you have to add appropriate transeries that will compensate for these pieces. So let me tell you how this goes. So the idea is that to this perturbative series, you will add additional pieces so that to make it a transeries. And in the case of this, yes? Is there a question? Okay. So here you have various transitive terms that I actually label as one instanton, two instanton, and so on. And this can be very computed very explicitly. So you see they have the structure of that I was mentioning before of the transities. They are exponentially small intercoupling constant, which here is g squared, and then they are multiplied. These exponentially small terms are multiplied by factorial divergent series themselves. And this is a one instanton correction. And notice that the two instanton correction has a piece which is imaginary. Okay, there is a piece which is imaginary and a piece which is real, which has the same structure. So I wrote here explicitly the imaginary piece because this is actually important from what follows. Okay, so let's consider then the sum of all these terms, and now let's do. Remember that each of these terms is a factorial divergent series, so let's do lateral Borel resummations for each of them. Okay, so let's actually consider the lateral Borel resummation of E0, the lateral Borel resummation of E1, the lateral Borel resummation of E2, and so on. Oops, sorry. Oh, there is something with my mouse here. It goes very fast when I. Okay, so let's look at this. So what happens when you do this? When you do this, you will get an imaginary piece due to the fact that you have deformed your contour, and this imaginary piece will be, say, positive or negative depending on your choice or lateral resummation. But remember that this two instanton piece is actually itself imaginary, okay, and it's also exponentially small. So you actually will choose the strength, or in this case, because of the coefficient I have fixed, this is just a coefficient plus or minus 1. The lateral Borel resummation of this part will actually cancel the one coming from the perturbative part. And actually, you have a full chain of cancellations in which every imaginary part that you get by doing lateral resummation will be canceled by a higher, a smaller, exponentially small term in this series. Okay, so here I'm showing you. Here I show you explicitly the leading cancellation, in which the leading part here is cancelled with the leading part here, but there is a kind of change of cancellations for higher orders. And it turns out that when you do the whole thing, this turns to be real. Okay, and this is kind of the general mechanism in which you can avoid you can actually do Borel resummations for series which are non-Borel summable. So the price you have to pay is to add these transeries by hand. Okay. Now this is supposed to be essentially proved by the people doing resurgence, the Laver, Dillinger, and Fan, but I don't know if this is actually the proof is completely rigorous. I mean, there have been issues by this, but this would be an exact statement. Okay, this is really kind of very far-reaching generalization of the standard proofs that, for example, were done for the quartic oscillator, because here you have to add all these instanton corrections. Okay. Now, what is interesting here is that when you do transities, you have to actually to pay various prices, and another price is that some of the exponential terms that you add are explicitly imaginary, even if your original series and your observable are real, because you need these imaginary pieces to kill ambiguities. And another thing is that the strength of a non-perturbative factor, of a non-perturbative correction like this, actually is ambiguous, because it depends on the choice of lateral resummation for the perturbative sector. So the way in which you sum your perturbative sector determines the coefficient of these non-perturbative corrections. And this is an important observation that was made by François David, which is a manifestation in a sense of the Stokes phenomenon, that the strength of non-perturbative corrections in theories with non-Borel summable perturbative series is not unambiguously defined. It depends on your choice of lateral resummation. Okay. Now, many of these things were developed by the French school of resurgence and the associated physics school, André Boros, Jean Saint-Justin, and this is, in a sense, the toy model for how to use transeries in more complicated settings. Okay. So this example, although it's simple, suggests that you can actually upgrade perturbative series to transeries and then obtain exact results by using lateral Borel-Legal resummation. Okay, and the hope is that this can be done maybe in more general situations. Okay, so you see the fact that the perturbative series non-Borel summable is not an obstruction. You have to consider these more general objects and this Borel-Legal type of resummation. Okay, so maybe that's a good point to stop for questions, because in a sense, what I'm going to do now is to try to kind of see how this program can be generalized to more general situations in quantum field theory.
Then can I ask a simple expected
Yes.
question? So what is the precise statement for this double whale case? So you add one instanton, two instantons, and many.
The precise statement is that there is a general transeries, which is going to be infinite, involving an infinite number of series of this type, okay, that can be computed explicitly. You can actually reproduce the exact, say, ground state energy for as a function of G by doing lateral resummations. Now, you can do either plus lateral resummation or minus lateral resummation. Both results will be equal, but if you choose plus equal resummation or minus equal resummation, you have to adjust the coefficients correspondingly, okay? So that all imaginary parts will cancel in the final result. That's the statement. And as far as I say, I don't know, I think this statement is, there are kind of suggestive proofs, but I don't think there is a totally rigorous proof yet of this statement.
Okay, thank you. So the result is not ambiguous. Okay.
The result is not ambiguous, absolutely.
Good. Yeah. Okay.
So you have to correlate your choice of lateral resummation with the coefficients that you put in the transeries, and that's a general phenomenon. That's in a sense the manifestation in this story of the Stokes phenomenon.
Another question, is this series summable? Because even if individual terms I can resum, now the sum, there is an infinite sum of instantons.
Absolutely.
Is it summable, or how can I prove this?
That's a great question, and this is in a sense one of the sources of problems. Now, in quantum mechanics, it's known that this series it's summable, and actually the way you can do it is, you can do it in you can actually deduce this result from WKB, and in WKB you can actually see that essentially this non-perturbative series can be give you essentially geometric series. Okay, so you can actually resum them, but it's a kind of very actually this is one of the open questions, that we don't know if this is the case in more general settings. But here in quantum mechanics, this is actually true. But you have to put your finger on.
I think you will return to it, but in quantum field theory, as a physicist, I would expect that it's not summable.
Absolutely, I will actually give you some examples in which this is summable. But yes, there are some indications that in general case is not summable. Also, I will focus on the cases in which it is.
Okay, thank you.
Let
More
me ask
questions?
Excuse me?
Yes.
Let me ask one question. I'd like to know how to determine these coefficients of these instanton terms. So you first do the perturbative expansion of the usual perturbative series, and then you will locate the location of the poles, which will give you the exponential of 1/6 g² or something like that.
Yes.
Then you try to do the perturbative expansion for the rest and try to match the orders of g's, something like that.
Let me first, in general, this is a very complicated problem. This is a problem of how to fix, you see here in this language, this is how to fix these parameters that appear here, right? Which we call transeries parameters. This is a very difficult problem in general. Now, but in quantum mechanics, this again can be solved by using what is called the exact WKB method, okay? So in that case, essentially follows from the connection formula that you usually that you can use in this XWKB method. So in that case, this is actually determined uniquely by a simple means. Now, the question again is how in quantum field theory this can be done, and this is also a non-trivial problem. But here, quantum mechanics gives you kind of toy model where everything works very nicely and can be determined uniquely. Okay.
Okay, thank you.
Okay. So maybe let me try then to tell you what happens in quantum field theory, so including non-relativistic models. Now the first, here is a place where we have not that many tools, so there are many conjectures and so on, and there are many kind of cases where people have studied. So to summarize the situation, essentially we know that the renormalized perturbative series in quantum field theory is also factorially divergent. So coefficients after renormalization grow factorially, and in addition, we know that in some situations we don't know, we expect to have non-Borel summable series. And a very important case are asymptotically free series. In asymptotically free series, sorry, again, this. Okay. In asymptotically free series, you have the beta function, which has a first coefficient beta 0, which is negative. But it has been conjectured by Parisi and Toft that there are Borel singularities in the positive real axis at the points that can possibly occur at the points d over 2 over beta 0, where d is an integer. Okay, so this is a kind of conjecture that was put by Toft and Parisi in the early 80s, which is the possible location of Borel singularities. Okay, and if this is true, you have Borel singularities here, then you will have exponentially small terms. Remember that every Borel singularity, gives you a potentially exponentially small term. Is going to give you terms of this form, right, where G mu is the running coupling constant at the scale mu, and these are actually, of the form lambda over mu, where lambda is the dynamically generated scale of the asymptotically free series. So these possible non-perturbative corrections are also sometimes called, because of these, power corrections. They are called power corrections because they go like lambda divided by the typical scale at which you are doing your calculation, okay, to some power d. Now, these are the possible locations that they conjecture. This doesn't mean that all these locations are going to be realized, but if they are real, if there are singularities at the positive real axis, they actually conjecture that they have to be at these locations. Okay. Now, the presence of this singularity can be verified, for example, by using large M methods. This is an approximation method that has the advantage that you can actually do reliable calculations. And another interesting point is that these locations are not due to instantons. Remember that in this double well example that we discussed, the trans-series and the exponentially small corrections that we found were due to instanton sectors in the quantum mechanics. They were due to tunneling between the two vacua. In this case, in the case of these singularities that Parisi and Toft conjecture, the origin of this is not supposed to be of the instanton time. And for this reason, Toft called these singularities with a new name. They call it renormalons. Okay. Now, you remember that all these singularities are always due to factorial growth of perturbation theory. And what people conjecture is that there are special diagrams when you do your perturbative series that lead to this factorial growth after integration over momenta. So usually the heuristics of this story is that the instanton type of singularities, the singularities due to instantons, like in quantum mechanics, reflect the factorial growth in the total number of diagrams. While these renormalons that Parisi and Toft identify are due to the growth of the coefficients in the perturbative series due to some special diagrams which grow factorially because of integration over momenta, not just because of a combinatorial growth in the number of diagrams. Now, in principle, there should be additional singularities also due to instantons in quantum field theory, but the evidence for these singularities is less clear, I would say, and and it's not the ones that I'm going to focus on in this talk. And let me also mention that this type of singularities, renormalon type Borel singularities, have been also found in the perturbative series on some interesting quantum many-body systems, like the Leaf-Liniger model, the Godin-Yan model, the one-dimensional Hubbard model. All these are integrable models in which you can actually calculate the perturbative series to very large order, and you can actually see that there are going to be Borel singularities in the positive real axis, and these are associated to the growth of some particular type of diagram. So this renormalon phenomena, which was discovered in the context of asymptotically free theories, also governs the perturbative series in some simple quantum many-body systems. Okay? So this was something that I discussed in some papers with my former student, Thomas Reis. I'm not going to talk more about quantum many-body physics here, but we can, if you have questions, we can discuss it later on. Okay, let me give you an example, a very simple example of this type of singularities that occur in quantum field theory. Okay, and in a sense, I'm going to give you what I think is the simplest example of such a renormalon singularity. And in order to do that, I'm going to focus on a very simple model. This is a two-dimensional quantum field theory, which is asymptotically free, and it involves just fermions. Is the famous Gross-Neve model. So the Gross-Neve model, in this realization, is a set of n Dirac fermions, so it has a UN symmetry. This is the Lagrangian you have. So you have n fermions. You have an auxiliary field psi, sigma, and then you have an interaction vertex between sigma, psi bar, and psi, or equivalently, depending on your taste, you can integrate out sigma, and this will give you a quartic interaction terms between fermions. So that's the content of the model, and it's a very well-studied model. It's asymptotically free, and then you can actually see if this picture of Parisi and Toft is realized. And so let's look at to a very simple observable. Let's look at the two-point function of the psi bar. So, this will have this form where sigma is the self-energy. And now let's do a calculation of the perturbative series, renormalized perturbative series for this self-energy in the 1/n approximation, okay? So the leading contribution in the 1/n approximation to the self-energy is of order 1/n, okay? And is given by this type of diagrams. These are the typical renormalon diagrams. So you have here, you have the fermion psi bar psi, and then, they exchange a particle sigma, and then you have a sequence of fermion loops of this type. Now you actually compute this, you can actually compute this diagram, say in dimension regularization, and then you find that you actually get the typical k factorial. This is actually the exact result. You just get k factorial, okay? And then you get the coupling at the renormalized coupling at the scale p times n. And this is what sometimes people call the Toth coupling, which is the coupling which is kept fixed when n is large, okay? So, and this is a 1/n result, okay? So there is clearly a singularity in the Borel plane. You think about the Borel transform of this series, you have k factorial, so you will have a Borel singularity in the positive real axis. So this is the simplest example of a renormalon. You see, you just have order, at each loop order, you just have a single diagram, but after integrating over momentum and renormalizing, this single diagram at order k grows like k factorial, okay? So that's the typical example of a renormalon. This is how this renormalon appears diagrammatically. As I said before, every singularity in the Borel plane should be thought as a smoking gun for a non-perturbative effect. But here, what people actually thought when this started, this is actually, as I said, this is an old story, and it was already pointed out by Parisi, that the non-perturbative effects due to renormalons are actually reflecting what are called condensates in the operator product expansion. So the way to understand this is the following. So here I'm computing this two-point function by diagrammatic methods, but I could also compute this two-point function by using the operator product expansion of the operator psi bar psi. So when I do this operator product expansion, the first thing I get is the contribution of the identity, but then all the operators of the theory will appear with some additional coefficients, okay? So this is the contribution of the identity, this is the contribution of psi bar psi, this is the contribution of psi bar psi square, and so on. Now, if I now take the vacuum expectation value, if you are working in conventional perturbation theory, you assume that all these terms are zero, and then what you get is this, and this term is what gives you the conventional perturbative series. Okay. But notice that if these vacuum expectation values are not taken to be zero, they will actually give you non-perturbative exponentially small corrections, because you see in an asymptotically free theory, all these things are going to scale like the asymptotically, like the dynamically generated scale to some power, which is actually the dimension of the operator, and this will have this form there. Okay, so if these terms are not zero, then they are exponentially small. And then what Parisi and then Schiffman, Weinstein, and Sakharov conjecture is that in the actual vacuum, the physical vacuum, these terms are non-zero, and what you are seeing here is actually a transseries where you have the transseries parameter is the kind of numerical value of these condensates, of these vacuum expectation values. You will have exponentially small terms due to dimensional transmutation, and then all these series are going to give the perturbative series attached to these exponentially small terms. So the operator product expansion after taking vacuum expectation values is going to give you mathematically a transseries. So in a sense, you can think about vacuum expectation values of operator product expansions as realization of the mathematical structure of transseries in quantum field theory. So remember that transseries were defined in this way, and you can now think about this as the structure underlying the operator product expansion. So this is the perturbative series, is the contribution of the identity operator, and then all higher operators are going to give you exponentially small terms. This is the Wilson coefficient. The series attached to this exponentially small term is what people call the Wilson coefficient attached to the operator product expansion. And the transseries parameters are non-perturbative numbers, which give me the value of the condensates in the non-trivial vacuum. Okay, so this was the idea that was pushed forward, was sort of proposed at that time, and now we can think about this as a realization of a transseries in quantum field theory. Okay. Now, well, this is essentially what I have just explained. You see, this, here you will have a series of coefficients, which are the coefficients of all these operators. So this Wilson of coefficients can be calculated with perturbative methods by using the OPE. But what they cannot be computed with perturbative methods are the vacuum expectation values itself. So there is here, the exponentially small term, which is proportional to the dynamical scale. And then you have here a coefficient, which is fully non-perturbative and encodes information about the physical vacuum. Okay.
A question.
Yes.
Maybe it's not the problem in 2 dimensions, but normally I would expect infrared problems with C of X connected to the condensate. Is it true or not?
No, I'm not really. I mean, if you compute, you say, people. I mean, let's put it this way. In the standard coursing, if you are doing the calculation, say on the nonlinear sigma model or linear sigma model, if you want to avoid infrared problems, you have to compute invariant operators under the symmetry group. Okay, for the nonlinear sigma model. Okay. Now, but in QCD, you don't. People have computed these coefficients systematically in a sense. Okay, so for example, you take the Adler function in QCD. So people have computed these Wilson coefficients for the Adler function, and as far as I know, there are no infrared problems here. Okay.
For non-abelian groups, I agree. It shouldn't be a problem. For abelian, I would expect.
Okay. Now for abelian, this is a different story here because already you don't have this picture of renormalons here. I'm not really assuming that we are doing an asymptotically free theory. Okay.
Okay. Thank you.
Yeah. But indeed, you would find infrared effects, infrared problems if you were considering, for example, a non-ON invariant function, 2-point function in, say, the nonlinear sigma model. That you would have infrared problems already, but that's already at the perturbative level.
Yes.
Okay, now can we give some evidence about this picture? How do we know that this is true? Because these are just words. And actually, when I started working in this problem, in this topic, I was surprised. Also, I'm not a rigorous mathematical physicist. I have probably higher standard of rigor than many of my colleagues in quantum theory, and I didn't find this picture. I didn't really. I mean, this was something that people repeated over and over, but it was not clear to me if this was obvious or not. And one way to actually try to understand these things, at least for me, is to kind of think about a model where you can do calculations explicitly and actually see if it's true. So one piece of evidence that we have that this picture is true is by using the 1/n expansion. Okay. Now I already used the 1/n expansion in the sense that I have actually here tell you that the leading contribution to the self-energy here comes from this type of diagrams. This is a large n statement, but this is a large n statement which is diagrammatic here, and classifying all the diagrams appearing in the theory by the power of n, and this is a diagram which goes like 1/n. But there is another way of doing large n. Sometimes people do not distinguish these two ways, so I'm going to talk about perturbative or diagrammatic large n, and then there is another approach to large n, which I'm going to call exact large n. Now, the exact large n approach is an approach in which you actually expand the path integral around a non-trivial saddle point of the large n effective action, and it's a totally different perspective. Now, when you do this, and this was actually what Gross and Neve did, and many other people did, but when you do this, this is maybe something that people do not emphasize sufficiently, is that order by ordering 1/n, when you use this exact large n method, every observable is given by a sum of actual functions. So at each ordering 1/n, the observables are functions of the renormalized Toff coupling. Okay, and so you don't really get asymptotic series. You actually get functions after renormalization, of course. Now, you can actually apply this to this quark self-energy. Okay, you take the quark self-energy of the Gross-Neve model, and using this exact large n approach, you actually get a different function, a different answer for this self-energy. So you get, first of all, you get a non-trivial quantity here, m, which is proportional to lambda, and which is the mass gap for this series. This is the mass of the elementary fermions. This is purely non-perturbative, so no wonder that we didn't see it in this calculation here. This was a purely perturbative calculation, and here m is non-perturbative. But now at 1/n, you will find actually two pieces. You will find a piece proportional to p and a piece proportional to m again. And these are actually functions of pi squared over m squared. So they are actual functions that you can actually plot. They are defined by integrals. And now you can say, so what is the relationship between this answer, which is obtained by using the exact large n method, and then this perturbative answer in which we saw the Borel singularity? Well, it turns out that these functions are actually Borel-Écal resummations of transseries. Okay, and this was pointed out in a very beautiful paper by Martin Benecke and Brown and Kivel for the nonlinear sigma model. In the case of Gross and Neve, it was pointed out in a paper I wrote with my former postdoc Miravillas. So this is a case in which this picture is totally, this picture of transseries is totally explicit. This is actually something that you can actually prove. I mean, this is not just a guess or a numerical statement. This is something that you can prove using Mellin techniques, Mellin transform techniques, and you actually get here an infinite sum of e to the minus 2n over lambda. You get power series here, formal power series in the Toff coupling, whose coefficients, some of the coefficients will depend on a choice of lateral resummation plus minus, and here you have your choice of lateral resummation plus minus. And of course, the total answer doesn't depend on your choice. This is non-ambiguous, and this is an exact statement. Now, of course, n equals 0, where you don't have exponents, you actually find that phi 0, which is non-ambiguous, is actually the perturbative series, okay? And then you can actually push the calculation to n equal 1, And this is something that you can do from this is a function that you calculate in this Sattler-Chen method, and then you extract this phi1, and then you can do an explicit calculation and show that the first non-perturbative correction that you find here, phi1, is exactly the one that comes from this 4-quark operator in the OPE. Okay, so this is a case in which, by using, in a sense, a order by ordering 1/n non-perturbative definition of the theory, you actually find that these functions have a transidious structure, and they actually match this transidious conjecture that people were mentioning about the OPE structure and so on. So this is a case in which this is totally clear. And you can also do the same for the 2-point function of the nonlinear sigma model. Okay, so in these 2-dimensional models, in the 1/n expansion, each observable which can be exactly calculated, that these are these observables that people have looked at carefully, are Borel-Ekal resum transeries. Okay, that's a fact of life. Now you can actually say, well, but working at large chain, in 1/n is kind of cheap. I mean, maybe all this is an artifact of the 1/n expansion. So can we give evidence that observables at finite n, in a finite n quantum theory, can be also given by resum transeries? Now the problem one finds when you ask these kind of questions, the problem one you have is very clear. You see, in order to tell you that an observable is given by a Borel-Ekal resum transeries, I have to have a non-perturbative definition of my observable. Okay, because this is a strong statement saying that when you do this Borel-Ekal resummation and you sum over all these non-perturbative sectors, you get a number which corresponds to the non-perturbative answer. Now, of course, in general, in quantum field theory, we don't have kind of many sources of non-perturbative definitions unless you go to the lattice. Okay, that's another story. So if you want to answer this question analytically, the first thing you have to do is to try to find quantum field theories in which you have non-perturbative definitions of your observables. Now, one thing you can do is order by ordering 1/n, use this exact Sattler-Chen method, which gives you functions at each ordering 1/n. But if you want to go to finite n, what you can do? Well, there is one thing you can do, and this is what Freeman Dyson recommended in the preface to this famous book, which is that when you are stuck and you are working on solvable problems, you have to do a trip to the beautiful world of one dimension, which will refresh your imagination better than a dose of LSD. Okay, so this was written by Dyson in 1967 when in the review on a book on exact results in one-dimensional quantum theory that was, I think, edited by Leaf and some other people. Okay, so and this drawing was included in the review, okay, in the article. So this was in Physics Today in 1967. So let's go then to the world of one dimension to see if we can refresh our imagination. And then one thing that you can realize is that the kind of quantum field theories that I discussed before, like the Gross-Neve model and the nonlinear sigma model, which are asymptotically free, can be solved with this exact Sattler-Chen method, but they are also integrable. Okay, their S matrix is exactly known. This doesn't mean that you can actually calculate observables easily, but there is one observable which was realized by Polyakov and Bigman that it can be calculated exactly. And this is the ground state energy after you couple the theory to a chemical potential H through a global conserved charge. So you take the Hamiltonian of your theory, you add a conserved charge coupled to this chemical potential. So you have a choice. You have choices here. You can choose many conserved charges, and you calculate the infinite volume limit of this log of the trace, and then you get a quantity which depends on H, and this I'm going to call the free energy from now on, and it depends on H. Okay. Now this quantity, it's very, very interesting. And I don't think it has actually people have looked at it carefully enough, but it has many beautiful properties. So let's look at it a little bit more carefully. Now, the first thing is the following. Remember that we are working with asymptotically free theories. Now, the nice thing about this quantity is that it has a scale. H, which is this chemical potential, sets a scale. Okay, and then in principle, if H is much larger than lambda, you can actually use perturbation theory, and you will get a perturbative series for this observable in the running coupling constant G at the scale set of H. So A and here are numbers that depends on the details of your theory, but this quantity has a well-defined perturbative series, okay, that you can compute with the standard methods. Now, on the other hand, as pointed out by Polyakov and Wigman, this free energy can also be calculated exactly by using the S matrix of the theory and the Bethe-Ansatz equations. Okay, and the whole answer for FH is actually encoded in an integral equation, which is of the Bethe-Ansatz type of equation. So let me actually show you here. So the calculation is actually very simple. It has two steps. First, you have to calculate what is called the Fermi density of Bethe roots. So this is a function E theta, which is a density of roots for the you are doing the Bethe-Ansatz, so there will be a density of roots, a set of roots, and then in the large volume limit, these roots will fill a dense interval. So you have this equation here. M here is the mass of the is a mass, the mass gap of the theory essentially. H is this external parameter, and this defines a function epsilon of theta. And the kernel for this integral equation depends on the S matrix. Can be computed from the S matrix plus an ansatz on the type of particles that appear when you turn on this chemical potential. So actually, if you want, this is a quantum field theory version of the type of integral equations that you find in the Lieb-Liniger and the Godin-Young model, for example. Okay, it's just a relativistic generalization of this. And then, the free energy of H can be calculated just by integrating this function epsilon of theta. And this is a totally perfectly well-defined non-perturbative definition of this quantity. Okay. Now, one can actually show by direct calculation that that this quantity has an asymptotic series which coincides with what you can calculate by standard methods in perturbation theory. This is a non-trivial statement, and I don't have a proof, but you can actually do it in examples and check that it works. Okay, but now the question you can ask is the following: well, can we actually calculate f of h, say, by Borel resummation of this series? Well, the picture you will find is very similar to the one that I was telling you before. The series will have Borel singularities in the positive real line, so you cannot just do a standard Borel resummation, but you have here an exact answer. So the question you can ask is, can we actually reproduce this exact answer by doing a lateral or Borelical resummation of an appropriate transeries? And the answer is yes. It takes a lot of work. You can actually find a transeries is actually non-trivial. You have to essentially decode this black box, which is this Bethe-Ansatz, and you find a transeries out of it. And this is actually non-trivial. Already the perturbative sector is very hard. And remember, if you're familiar with the work of Lieb and Liniger, remember that in the Lieb-Liniger model, it's very hard to actually extract the standard perturbative series from the integral equation. So here is also one of the problems that you find. But this problem can be eventually overcome, and you can actually get the full formal transeries, and you can actually compute it analytically to any desired order from the Bethe-Ansatz equations. Okay, and then you get all this information, and there is extensive numerical evidence, but very far from proof, that the exact answer for this free energy can be obtained by lateral Borelical resummation of this transeries. Okay. Now let me point out that this observable is not a product of operators, so you cannot use the operator product expansion. So here we don't have this operator product expansion picture, but still we have this transeries picture in which this observable can be obtained by a resummation. Now, let me point out that this is also one case in which instantons are also relevant, because this structure applies to nonlinear sigma model, ON nonlinear sigma model, and Gross-Neve, and in particular, the O3 nonlinear sigma model has instantons, has stable instantons, and this was one of the results that I actually found very very beautiful is that you can actually, when you decompose this into a trans-series, you have the perturbative piece, you will have non-perturbative pieces, and here you actually get both these renormalons, which are ambiguous, and instanton contributions. So the trans-series will have a renormalon part, which is ambiguous, but then you will have an instanton part. And this is a rare example of a non-supersymmetric quantum field theory where instanton corrections can be determined to all orders. Okay, so you can actually find the instanton corrections very explicitly. So this is really very beautiful models for quantum field theory in which you see essentially all kinds of things. Okay, now I think I'm on time, so let me try to give you my conclusions on open problems. So I think, the fair statement is that there is some evidence that observables in quantum field theory can be represented as Borel-Eckert resum trans-series, at least in some cases. So this picture of the double well in quantum mechanics can actually be generalized. And in some cases, we understand this trans-series very well. For example, when you have operator product expansions. In some other cases, we can deduce them from the Bethe ansatz, but the trans-series that we obtain, for example, for this FH, I don't know how to deduce it from first principles. I mean, if you don't give me the Bethe ansatz, I don't know how to deduce it. I mean, in the other cases, in Grosneve case that we discussed before a large chain, I can actually map this result to the operator product expansion, but here there is no operator product expansion. So this is, for me, it's actually quite interesting because it says that in principle, you cannot, we don't really know how to calculate trans-series in all cases. I mean, there are some cases in which this is not really known. So this is the formal construction of trans-series in quantum field theory is not completely understood. Okay. Now, there is something that we cannot really understand in any case, and this is related to one of the questions I got before, is that the trans-series coefficients appearing in quantum field theory, so the numbers that multiply the exponential corrections, are genuinely non-perturbative. Okay, so these are really giving you information about the backing of the theory, and this, is not really accessible unless you have an exact solution. But you just give me the Lagrangian of the theory, I'm not going to be able to get them. There is a kind of people have been trying to relate these coefficients to things that you can calculate from lattice. Okay, so the most promising direction is to try to find a lattice realization of these trans-series parameters, so that you can at least, so if people in the lattice give you these numbers, you can still compute these trans-series expansions. Okay. And now a problem that was mentioned before is not clear that the series of non-perturbative corrections, because you have to sum an infinite number of terms, this actually converges. Okay, so after Borel resummation, each term in this series is a number or a number with some ambiguity, but will cancel in the end. But it's not clear that the full sum converges. In the examples I have discussed, this is known to be the case. So, for example, in these large chain examples, this is known to be the case, but it's suspected that this is really an artifact of the 1/n expansion. Okay. Now, in the case of this free energy that I discussed, there is some evidence that this also converges, but this is a very special observable. So, so there are arguments actually that this, for example, the OP diverges in general, and this means that you would need another layer of resummation methods. So it's not enough to do Borel resummation of the perturbative series and of all the series appearing in the trans-series, but you will have to have also another layer of resummation for that, for the series of non-perturbative corrections themselves. Okay, but this is something that has not been really explored in detail, and especially has not been explored in toy models, because in toy models this problem doesn't seem to arise. Okay, so I think that's all, and thank you very much for your attention.
Thank you very much for a very clear and interesting talk. Are there more questions or remarks?
I would like to ask a question, namely, if we have, for example, pure gluodynamics, pure gluons in SU3, then we will have the condensate like G mu nu, G mu nu. How to get a scale out of these trans-series? Because that's a major problem. G mu nu has a scale, while it is not given by the Lagrangian, because it's conformally invariant. how to get a scale out of this e2 minus 1 over g squared or whatever? How to get a number out of this?
Well, I mean, you don't get. I mean, you cannot get a number, but what you can get is. I mean, you know that this is going to be proportional, right? Just by renormalization group arguments, you know that this is going to be proportional to lambda, to the scale, right? I mean, you use the RG, the renormalization group argument to show that all these condensates are given by a power of lambda multiplying a power series in the coupling constant, okay, which is given by these Wilson coefficients. And then what you don't know is the exact coefficient, the numerical coefficient that you get there, right?
Okay.
That's what you don't know.
I know. Yeah. So you can have the, I don't know, the cutoff scale lambda to the fourth, for example.
Yeah,
but how
exactly.
to get the number that it is
no, the number,
that's
absolutely. The number, the only way I know how to get this number is by, I mean, either by fitting it. Okay, actually, the original idea of the sum rules of Shipman, Weisstein, and Sakharov is that, okay, I have this trans series. This describes this observable beyond perturbation theory. So now I can just look at the data and try to extract this number. This was like very rough, but this is something that they did. And now the idea that people have been trying to do is, okay, can I actually extract this number from lattice simulations? Well, in lattice simulations, you cannot really simulate these correlation functions. But for example, now people are trying to reparameterize this operator product expansion by using some sort of form of the operator product expansion that you can do in the lattice, and then eventually mix both things. But I agree with you that, in principle, these numbers have to come from a non-perturbative definition of the theory. These are not numbers that you're going to get from perturbation theory. Right?
Okay, so in trans-series, I have the same problem as in perturbative, so I have to compare with the experiment, in a sense, to get the numbers right.
Yes. I mean, the thing is that the thing is that you can actually, just by giving me a discrete sequence of numbers, you can parameterize an infinite number of processes, right? Because the dependence. Yeah. So here, for example, you see here, here you give me some numbers, and then the dependence on the momenta are totally fixed, right, by these Wilson coefficients, which in principle can be calculated with perturbative methods. Okay,
but the numbers have to be taken from elsewhere.
From somewhere, absolutely.
Okay.
Trans-series.
The
trans-series
same problem
method
as in perturbate. Okay.
Yes.
Thank you.
So, any other questions?
Sorry, can I ask a generic question?
Sure.
Go ahead. Yes.
So I want to ask a certain inverse problem. Suppose you have a full trans series. Then can you derive a partial differential equation which is satisfied non-perturbatively if it exists?
Yeah, that's a very good question. But in general, as far as I know, there are no in the examples I discussed in quantum field theory, there are no the information of the trans-series is not encoded in an ODE, but maybe just because people didn't try hard enough. So the closest thing is in these integral models where the information is encoded in an integral equation. So here you have the full trans-series is encoded in an integral equation in a very involved way.
Yeah.
But this picture that as I said before, when you have nonlinear ODEs, people have methods to actually manipulate and calculate these trans-series, but in quantum field theory, you don't have such a picture that I know.
Okay.
Okay, any other questions? Then maybe following up on Krzysztof's question, essentially you told it, but could you explain again how the mass generation in Gros-Neveu model comes out from this trans-series approach?
Well, the trans-series doesn't really give you the mass generation. I mean, what happens is the following. I mean, let me see. Yeah, this is a purely non-perturbative result. Okay, this is a result which is non-perturbative. This is not what comes from transseries. What you know is that this result can be obtained as a resummation of a transseries, and most of these transseries can be calculated from the OPE. But that's the statement. Okay, so you don't really have for example the mass here. Okay, you can think about this as the first term in a transseries, but this is something that you cannot really the exact value of the relationship between m and lambda. So the exact quotient, m divided by lambda is a pure number. Okay. That's not something that the transseries approach will give you. The transseries approach will give you the dependence on the momenta for that function. Okay, but so here there will be numbers hidden here which you cannot get, but you get essentially most of the information from the transseries. At least.
So the philosophy is you first need to have a solution from somewhere, and then you can prove that it comes from a transseries. Or?
No, the way people have done. I mean, no, there are various. There is a question of. There is one mathematical question which is given. If I give you an exact observer in quantum field theory, can I represent it as a Borel-Resum transseries? That's one mathematical question. Now, the practical question is, you give me a quantum field theory and you want to do a calculation beyond perturbation theory. What should you do? Okay. Now, there is what people did essentially with this OPE. The OPE method gives you a way to do that. And essentially, it gives you a way of you calculate this OPE. Most of this OPE is, you can do it with perturbation theory or with variants of perturbation theory. I mean, the perturbative series here is just the first term. By these Wilson coefficients can be computed with perturbative techniques. And then, you get a transseries. And what you don't know are the coefficients. The coefficients, you assume they are purely non-perturbative. And then what you can do, and this is what people did in this sum rule philosophy, is that they fix these coefficients. They try to fix them with data. And then, you can use this, for example, to get, to get a kind of empirical transseries that you can use to calculate other things. Okay, that was the approach that people follow. Now, the approach that people are trying to do now is, okay, I have a transseries. That's what the transseries, for example, in QCD, for example, what this is telling you is the following: you are working at very high energies. This is the leading contribution given by the perturbative series, but there will be non-trivial corrections given by this transseries. So even in high energy QCD, these terms can be very important. So what you try to do is you try to get the coefficients by, say, a lattice calculation now. Okay, so this is something that people are trying now to do. Okay, so to parameterize the transseries is parameterized by these coefficients, and then you try to relate this to some lattice calculation from which you can extract them. Okay, that's
so transseries give you like a general structure of your solution, and then you need input from elsewhere to fill in the details.
Exactly. The transseries gives you a general parameterization of non-perturbative observables. But then the coefficients that you have there have to come from somewhere else. You are not going to get them from purely perturbative methods.
Okay. I see.
But can it happen that I have transseries and I cannot attribute a given term to any reasonable condensate?
Absolutely. In principle, the philosophy that people have been using is that you give me a transseries, and then people try to have this kind of one-to-one correspondence between a condensate and an exponentially small effect and some physical effect. Okay.
Yes.
And this is the philosophy that people have used. And for example, when you have an OPE, that seems to be reasonable, right? Because after all, the OPE has this structure. But now let's consider, for example, FH here, right? FH here, you see, here I cannot use the OPE. So I have here some kind of complicated transseries, And already, you see that what people call instanton and renormalon effects are mixed, you see?
Yes.
So this already, you have to disentangle this, and this is already tricky. Now, this thing that you could say is a renormalon, here you cannot really associate it to a condensate in the same way that we did it before, because this observable doesn't have an OP. It's not the product of operators, right?
Yes.
It's a free
Yes,
energy.
exactly.
And
that's my
the same
question,
thing happens, say, for example, ground state energies, quark masses, there are many quantities which are well defined in principle in beyond perturbation theory, but cannot be decoded in an OP. And this is one of the open problems. For this series, you cannot even use perturbation theory in principle to do a calculation of the transseries. We really know very, very little about transseries in quantum field theory. The OP gives you a kind of big handle on it, but doesn't really exhaust the whole wall of transseries.
That's how I understood Hooft, renormalons, that they are kind of collective thing that cannot be attributed directly to a given condensate or whatever coming from the elementary fields.
Well, I would say that when the observable has an OPE, you sort of you should be able to do it, right? I mean that because the structure of for a product of operators, the OPE tells you how the renormalon should match these things. So, for example, here in this example in Gros-Neve, this was a kind of very non-trivial calculation we did. We actually got the transseries from the exact answer, and we actually saw exactly that this transseries was coming from the 4-quark condensate. So this is a non-trivial check that, here the transseries seems to be in one-to-one correspondence, as far as we know, with the operator product response. This you can check.
But endpoint functions are not the only observables we have.
Absolutely. That's what I mean. That's what I mean.
Yeah,
For
if
things
they
which
are not
not
of this form,
absolutely.
they cannot be probably attributed to any.
Exactly. That I totally agree
my
with
question,
you.
that they are not the only observables we have.
Absolutely. For as I said, for the free energy, we don't know how to map them to condensates.
Exactly.
Also, they have the same structure. I mean, you will also have exponentially small things involving the first coefficient of the beta function. So the conjecture on the location of singularities works relatively well to locate the singularities, but then you cannot associate it to condensates in a clear way.
Exactly, that was my question. Yes.
So on that front, we haven't done many. We don't have progress. We have examples of how to extract transseries which do not correspond to OPE, but we don't have a method to compute these transseries independently.
Okay, thank you.
Okay, any other questions or comments? If not, let's maybe thank the speaker again.
Thank you.
And stop the